Okay, in this example, we're going to be doing a 2-block problem, just like we did in example 5 for the 1D motion. So here we have 2 blocks, one of mass MA and the other of mass MB. They're tied together with a massless rope. The mass of block A is 1/5 the mass of block B. Block A sits on the table with a coefficient of friction of mu sub k. Block B hangs from a massless resistance-free pulley. That's important for us to know. The blocks are released from rest. A, find the tension in the rope, and B, find the acceleration in terms of the masses and the acceleration due to gravity. Now, this is actually the same as example 5, except we're adding a horizontal direction to one of the blocks. We could also, once we learn about inclined planes, we could add an incline to one of the blocks or both of the blocks. They're still considered Atwood machine problems, okay? And that means just 2-body problems connected by a rope. So that means we're going to be using the same assumptions we did in the previous example, example 5. We're going to be assuming that the massless rope is going to have the same tension throughout the rope. We're going to assume that that tension is the same for both blocks. And therefore, since both of the blocks are connected by that rope, we're going to assume that the acceleration of both of the blocks is the same magnitude. Notice I said same magnitude. The accelerations are going to be in different directions. So that means the acceleration will not be the same. We have to be very careful about how we say these things. Okay, so the acceleration will not be the same, but the magnitude will. And the only reason for that is that the direction is different. Okay, so the first thing I want to do is I want to go ahead and draw a picture of this so I have in my head what's going on. Okay, so I have a table and I have a block sitting on the table. I have a rope on the block and I have it attached to a pulley. I have another block that's connected to the other end of the rope. Okay, this is block MA. And this is block MB. We know that MA is 1/5 the mass of MB. And so that tells me that instead of these blocks just hanging there, that block M is going to move this way and block A is going to move this way. Okay, so I'm going to have to draw my diagrams separately for each object. So when we look at block MA, we're just looking at MA, and when we're looking at MB, we're only looking at MB. And this is where your knowledge of the F on A by B notation becomes important, because we don't have to worry about the pulley, this, that, block A acting on block B. We just cover this up and we say what's physically touching MA, what's physically touching MB. What's acting at a distance? What's acting at a distance? Okay, it separates the problem out for us and it reduces all of that anxiety that other students have when solving these types of problems. Because looking at this problem initially, you might be thinking, oh my gosh, how am I going to do this? This is complicated. But when you just go back to what you've learned in the inquiry and just take it one step at a time, you're going to see how easy this is. Okay, so what I'm going to do is I'm going to fold my paper in half. Okay, now here's the trick for this. Normally I would have X here and Y here, but what I'm going to do is I'm going to have block A and block B, and I'm going to do X first here, and then I'm going to do Y underneath it, just so I have enough room to solve the problem. Okay, now a lot of you may be thinking, wow, we're going to use a lot of paper to do this. Yes, that's true. But the reason why I write out all the steps is so that you understand exactly what's going on, so that when you go to reproduce the problem, you'll understand why you're getting the answers you're getting. Okay, so let's look at block MA first. The first thing I'm going to do is I'm going to go ahead and draw a motion diagram and a free body diagram. Okay, so the first thing I'm going to do is I know that block A is accelerating. to the right. So we're going to go ahead and do that. So it starts from rest. Okay. Okay, so there's my velocity. And now I need my acceleration. Okay, so there's my acceleration, and now what I'm going to do is I'm going to draw my free body diagram. So what's physically touching block A? The table. Anything else? The string. Is the table rubbing, supporting, or both? It's actually doing both. Well, let's see. Yes, because they're giving us the coefficient of friction, so there is friction. Okay, so we have a support, we have a frictional force, we have the tension in the rope. Anything else? Okay, so what's acting at a distance? The Earth. Are we in equilibrium? No, we're not in equilibrium in the horizontal direction. Vertically, yes. Horizontally, no. So let's go ahead and draw our dot. Okay, and now what I'm going to do is I'm going to go ahead and draw my weight and my normal force. And I'm going to make my tension longer than my frictional force. Okay, so this is force on block by table. This is force on block by earth. This is force on block by rope. And this is the frictional force, force on block by table. Okay, so there is our free body diagram. Now we're ready to go ahead and sum the forces. So the sum of the forces in the x direction is equal to max. We're going to go ahead and substitute in from our free body diagram in the x direction. So I have the frictional force, force on block by table, plus the tension, force on block by rope, and that's equal to ma sub x. Okay, am I accelerating in the x direction? Yes, I am, so I'm going to keep this, Newton's first law. Okay, so now we're going to substitute in magnitude and direction. So I have minus mu sub k times the magnitude of the normal force, force on block by table. Now you may be saying, wait a minute, Dr. H, you just put a vector sign on that. Yes, I did, but I also put absolute value bars. I'm writing this different ways so that you understand all the ways that you can indicate a magnitude. Okay, you could completely remove the vector sign, or if you're going to write the vector sign, you put the absolute value bars, which says that you ignore the direction. Okay, so this is I hat plus force on block by rope, and that's, I hat, and that's equal to m sub a I hat. Okay, do I have the acceleration? No. Do I have the tension? No. But I can cross out my unit vector, so let's go ahead and do that. I have too many unknowns. I also don't know the normal force. So I need to go ahead and solve in the y direction. Again, I'm not going over because this is where I'm going to put mass B. Okay, so mass A, sum of the forces in y is equal to ma sub y. Let's go ahead and add up all the forces in the y direction. I have force on block by table plus force on block by earth, and that's equal to ma sub y. Am I accelerating in the y direction? No, so that's 0, Newton's first law. Be very careful with this. You really do have to think about it. You can't just say yes or no. Okay, make sure you're verifying by looking at your motion diagram or looking at your free body diagram. I can't tell you how many times I've seen students say, yes, there's an acceleration, but not actually have written this and having not really checked their diagram. Yes, you're accelerating, but remember, this is the y direction, not the x direction. Okay, you still have to be careful with this and make sure that you're only accelerating in the correct direction. Okay, substituting in our magnitude and direction, we have force on block by table, j hat minus m sub a g j hat equals 0 newtons j hat. Notice the subscript for the mass. Please make sure you are using subscripts when you have multiple masses, because if you don't, you're just going to have m's everywhere. And when you go to combine the b equations with the a equations, it's going to get confusing. So you need to make sure that you're not missing subscripts. We're going to cross out our unit vectors, and oh, I'm sorry, this should have been minus, not equals. Okay, and now we're going to add this to the other side. So force on block by table is equal to m sub a g. Now I can substitute this in up here, but I'm not going to do that just yet. I'm going to call this equation 1, and I'm going to call this equation 2. I still have more unknowns. I know this one now. Okay, check. But I still don't know the tension, and I still don't know the acceleration. I have 3 unknowns in this equation. 1, 2, 3. I only solved for 2 of those so far. Or actually, I've only solved for 1 of those 3. So I still have 2 unknowns. And that means I need another equation. I need 3 equations. So now I'm going to look at mass B, the mass that's hanging from the string. Okay, so am I in equilibrium? No, I'm not. So I'm going to go ahead and draw my motion diagram. Be very careful with this one, because you're accelerating down. Okay, and notice that I have this being the same length as this, as it should be. Notice that I made the tension here 1.5 centimeters. That means I need to make the tension over here 1.5 centimeters. Remember from the last problem that because it's the same piece of rope, you're going to have the same tension. Okay, so let's go ahead and write that out. So we have 1.5 centimeters going up. Okay, and the difference I made here was, let's see, that is about 1.5, and that's about almost 1, well, 8. So what we're going to do here is we're just going to draw this longer by that much. Okay, so this is force on block B by earth, and this is force on block B by rope. Okay, now this makes it a little bit easier because we're only in one direction. Okay, so we're going to go ahead and do some of the forces. In the y direction is equal to ma sub y. We're going to go ahead and substitute in from our free body diagram. So we have force on block by rope plus force on block by earth, and that is equal to ma sub y. Am I accelerating in the vertical direction? Yes, I am. Newton's first law. Okay, substituting in magnitude and direction. And I'm sorry, this is block B. So I have force on block B by rope minus M sub B G J hat. Oh, sorry, I got to get rid of that vector sign. This is why you shouldn't write in pen. And this is equal to negative MVA J hat. Notice that I had to put a negative J hat here. That's because the acceleration is pointing down. Notice also that I substituted in M sub B because that's the mass of block B there. Okay, cross out our unit vectors. Now, I have two options here. I can solve for the tension or I can solve for the acceleration. I have really two equations, two unknowns. So when you have two equations and two unknowns, you can solve by substitution or elimination or any of those. So what I'm going to do is I'm going to rewrite these three equations separately. And then what we're going to do is solve for the unknowns. Okay. So let's rewrite these equations. I have minus mu sub k times F on block by table plus force on block by rope is equal to M sub A. I also have force on block by table is equal to M sub A G. I also have force on block B by rope minus M sub BG is equal to minus M sub BA. In the next video, I'll solve for these three, for the three unknowns.